Okay, welcome back. Now, we start to go to another topic about shear stress. As you know, this is actually is the actual load, But you remember I tell you before, the stress depends on the phase it act on. That means for this here, you say this is a normal stress because the plane is here. But if the plane is here, like here, should be not a normal stress, should become shear stress here. And repeat again, the same loading, actual load. But if the load applied on the plane, we call normal stress. But the same loading on this kind of plane here, and we can only say it is a shear stress because on the different plane. So the plane here is a normal stress. The plane here is we call it a shear stress. That means the boat, this area is subject by shear stress. But for the rod here is a normal stress. So the same loading here is a normal stress, but here is a shear stress due to different kind of plane. Different kind of plane here. So very important. Another thing is shear force different from shear stress. Shear force here and the shear stress you need to divide it by the area. So shear stress equal to shear force divided by area. The area is the cross section here. Something like that. If the loading here, but if the plane here, so this becomes shear force on here, and the shear force, and there is also a constitutive law. We mean shearing strength equal to shearing stress divided by modulus. We call shear modulus. So when actual stress, normal stress, the Young's modulus, the constitutive law, sigma equal to Young's modulus multiplied by strength. For the shearing, the shear stress equal to the shear modulus multiple gamma. Gamma is the shear strength. And if this is an isotopic material, maybe you will learn if it is a composite material, is not equal. But if an isotopic material, these two values has a relationship. Shear modulus equal to Young's modulus divided by 2 and 1 plus Poisson ratio. I remind you, if the material is an isotopic material, is follow this relationship. If the material is not isotopic, it should be not equal. When you study in master degree, you will discuss about this as what kind of case is equal. What kind of case is not equal. But in our topic discussed here, all the material is isotopic, so it should be equal. Now, when we're talking about shear stress, we need to introduce the idea 3D, X, Y, Z, 3D stress tensor. What is a stress tensor? If this is a material, and this material subject by any kind of loading, actual load, bending, or rotation. And then we just take an element to look. This element, it should be have 9 components. As you remember, I already tell you before in the previous course, the 3 is a 3 dimension. And the second is because we talking about is a parameter of determination. The stress determined by force and determined by the area. So it's a 2 parameter. So 3 Q equal to 9. 9. We can get the 9 variables. We can get 9 variables. We may look video and you will know better.
Explain the 3-dimensional stress tensor. In order to understand what a 3-dimensional stress tensor is, consider an arbitrary body subjected to different forces. Due to these forces, stresses get induced in the body in all the 3 dimensions. Let us consider an infinitesimal stress element which shows the state of stress at a point in the given stressed body. Assume that the stress element is in equilibrium. We see that this stress element,
the meaning of equilibrium is we discussed before equilibrium equation, because a load applied and it responds the stress on the element
consists of 6 faces in the 3 dimensions. The face perpendicular to the positive direction is called positive face.
Positive face means positive if the face here and the direction here, and the direction the same as the x, we call it a positive. That means this is a positive because the normal direction here is the same as the y. The normal direction here is the same as z. The normal direction here is the same as x. So we call this is a positive area.
And that to the negative direction is called negative phase.
Negative phase is when you look this direction here is a negative to x axis, and this direction here is a negative to z, and this direction here is a negative to the y. So we call this a negative phase.
Now the stress element is subjected to 3 different normal stresses and 6 different shear stresses. Thus, to define stress at any point in a 3-dimensional space, we require 9 components of stresses, which can be represented in the form of a multi-dimensional array as shown. Such array is termed as a 3-dimensional stress tensor. Thus, a 3-dimensional stress tensor is a multi-dimensional array of 9 stress components. Now let's discuss about the nomenclature and sign convention for these stress components. Let's start with normal stress. It has a subscript that identifies the face on which the stress acts. For example, normal stress sigma x is acting on the x face of the element, and the normal stress sigma z is acting on the Z face of the element. The sign convention for normal stress is very simple. Tensile stress is taken as positive, while compressive stress is taken as negative. Now let us discuss about the nomenclature and sign convention for shear stress. It has two subscripts, where subscript 1 identifies the face on which the stress acts, while
subscript here you just remind the first subscript is the meaning of the face, and the second is the meaning of the force direction. So you just remember the first subscript is about the face, and the second is about the force. So this is a face, and this is the force.
Subscript 2 identifies the direction of stress on that face of the element. For example, shear stress tau xy is acting on the x face of the element. And
so tau xy x is the face. So the face should be here because this is a x. This the face is belong to x. Why the face belong to x? The meaning is the face, the normal direction is the normal direction of the face is x. The normal direction of the face is x. So the subscript is the face for the face, and the y is the force. So the force is this direction parallel to this direction. So it's a y.
In y direction. And the shear stress tau zx is acting.
Again, G is about the face. So you see the face here, the face here, the face here. The face here, the normal direction is along the G. So we call the face is G. And the loading, you see, is along the x direction. So we call it a tau gx.
On the Z face of the element and in the x direction. Shear stress is positive when it acts in the positive phase and positive direction of an axis. It is also positive when it acts in the negative phase and negative direction of an axis. Thus, in this given stress element, all the shear stress components are positive, and a shear stress is negative when it acts in the positive phase and in the negative direction of an axis. It is also negative when it acts in the negative phase and positive direction of an axis. Related terms are:
okay, now it's easy for you for understanding. Could you please take your pen? Yeah, please take your pen and write down. Follow me. Actually, it is very important for your understanding. For stress, this is the tensor. So it's a 3 multiple 3. So totally we have 9 components. Sigma yx. You should write down. Follow me, and it's good for your understanding. This is 9 components, 9 variables. The definition, we say sigma we may use maybe use this idea. Okay, sorry. I think it's not easy for you to understand it, so we may change. We say sigma xy, for example. And about sigma x. Sometimes this is a shear, and we call it a normal stress. And we also have a shear stress, normal stress. So shear stress, we also write down like this. And normal stress, we always neglect one subscript. This is just an example. The force, because we know always the sigma is equal to the force by area. So sigma ij is equal to the pj and the ai. The idea is the p, the force direction direction along y axis. And the normal direction of the action phase along x-axis. So you should know is x is for the action phase, and the y here is about the force direction along y. So very, very important for you to understanding the meaning. So in this case, please you may follow this rule. Follow this rule. The force direction along force direction along x axis. And the normal direction of the action face, or you can also say plane, along x axis. So we say here we say x-axis. What is the normal if the face, this is the face, or this is the plane, and we say this is the perpendicular, is a normal direction. Of plane. So the normal direction of the plane, it means the plane, the vertical direction, we call it the normal direction. So when you see the normal direction, the normal direction of axis, that this is axis, x-axis long. Okay, it's you may practice. So now we have done. Please practice by yourself. Sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma gx, sigma gy, sigma gz. Please, everybody, write down by yourself as the format, as the format like this, as the format like this. So everybody, you should write down the nine variable, write down the 9 variable, and follow this format, and become your practice. Everybody should write down 9 for me during the practice time.